Hello, everybody, and welcome to our webinar today, Real Queryable Encryption for PostgreSQL. Delighted to be here with you guys today. We're about to get started. Just before we do, a couple of quick housekeeping items. First of all, this webinar is being recorded, and you will get a link for the on-demand version right after the webinar. Also, we're going to make this webinar as interactive as possible, so there's going to be a couple of things along the way. First of all, there will be some polls that will pop up on your screen during the course of the webinar. You'll also see the polls tab in the bottom right-hand side of your screen that you can use to check for the polls and the results at any point. Also, please feel free to ask or submit your questions at any point. We're going to be taking questions via the text with the questions tab, also right next to the polls tab there in the bottom right of your screen. And we will be answering all of the questions at the end of the webinar. So with that, I'd like to hand things over to our speakers to get us started. So back over to Sushant Rao. Sushant, all yours.
Great, thank you so much, Roz. Everyone, thanks for joining us today. And let's start by having our main speaker, Billy, introduce himself. Billy?
Thank you. Yeah, I'm Billy Van Cannon. I'm the Director of Product Management here at Baffle. I've been in various aspects of security for almost 20 years. I worked in various places, including encryption, but also a lot of identity and access management. I have my MBA from Kellogg, and I have a bachelor's in electrical engineering from Iowa State University.
Nice. Well, thank you for taking the time to join us today, Billy. And then, hi, folks. Let me introduce myself. My name is Sushant. I run marketing at Baffle. Been with the company for a few years. Most of my background has been in software and cloud services, primarily in the infrastructure and security and data spaces. So let's go through our agenda for today. So we have a kind of a packed agenda, if you will. We're going to cover, first of all, the current state and risks in the market. I'll talk about transparent application level encryption. You may have heard of application level encryption, but there's a new way of doing it that is going to be much easier and simpler to do application level encryption. Then talking about operating on encrypted data, which is, I think, the main thing that a lot of you folks are curious about. Then we'll talk about compliance and least privilege. Then we'll go into a deeper dive into real queryable encryption, also known as RQE. We'll do a demo of RQE, and then we'll cover questions. So with that, let me turn it over to Billy to talk about current state and risks.
All right, great. Happy to be here, and I'm excited to get started. So current state and risk. So we could put up slide after slide of fear, uncertainty, and doubt, but the latest headline, I believe, is Snowflake attacks. One of the largest data breaches ever. That happened a couple months ago. It was disclosed a couple months ago, and then AT&T breach happened and brought it right back into the headlines again. And on this one, Snowflake victims, they either used weak passwords or their passwords were stolen, through social engineering like phishing, and or they didn't have multi-factor authentication on them. And so when I hear this, as somebody who's been in security for almost 20 years, the thing that strikes me is that the end users are just never going to care. They will always have weak passwords. They will always be susceptible to social engineering. They will always try to bypass MFA if they possibly can. And I don't blame them. They're lawyers, they're accountants, they're salespeople. Security isn't their main thing, and they just want to do their job. So Baffle believes that encryption's the answer, at least a big part of the answer. But how it's implemented is critical. But if it's done properly, the encryption can follow the data. And so what I mean by that is, like, if you have a production environment and you put all these access controls on it, passwords and MFA and firewalls and the whole 9 yards, and a test engineer comes along and copies all that data into another environment, all those access controls are worthless, except in encryption. Encryption goes with the data. And that also is backed up by all the security and compliance frameworks. We'll talk about a few of them, but GDPR and all the US state level privacy laws explicitly state that stolen encrypted data does not have to be reported and is not subject to fines. So how data is encrypted will be a major theme in this webinar. So along those lines, one of the things you're supposed to do in security is figure out what your attack vectors are and then how you're going to defend against them. So I started with this report from IBM, the Cost of Data Report 2023. Of course, they have one every year. And, you start looking at this, stolen and compromised credentials. So there's, what happened to Snowflake. And that's at 15%. So it's one of the highest ones. The highest one they have is phishing or social engineering. But when you break that down, what are they trying to steal when they do phishing? They're trying to either trick you into handing over your credentials, or they're trying to give you a link to download malware. And malware is not even on here. But so some big percentage of this is the same as stealing credentials, and then some other percentage of it's malware. And then there's another one for social engineering, which phishing is just an aspect of social engineering. So you could add more, credentials and malware to that. So credentials is a pretty big one. We'll also talk about cloud misconfiguration and the software patches. But what I try to do is take those and map them into this grid, and specifically how encryption can help. So we have these threat vectors that, like I said, I kind of massaged and pulled over. And then I try to determine who would be responsible for that. So like a physical stolen disk drive, only a criminal would do that, right? Like your database admin is not stealing the hard drive, but the database admin is in charge of their credentials, log access, and they could be a malicious insider, which is over here. So kind of going through that. There's also a cloud infrastructure administrator. So if you're trying to outsource to the cloud, which we'll talk quite a bit about, there could also be a cloud misconfiguration along with that. So I added that to the threat vectors there. This one is very specific to Baffle, and I'll talk more about that. The threat vectors aren't even on here, but I just wanted to point out, I'm being open and honest about Baffle's solution and how, all the strengths and weaknesses of it. So I have that in there. And then duplicate environments is not a threat vector, but it's, as I talked about with the production and how data is constantly being copied to all these other environments, you have to bring your access controls to protect against these threat vectors. So I broke that one out as well. And this is all on how the database could be attacked. I'll talk about the application later. And so just to kind of really dive in here, to use a first example, we'll talk about database side encryption. And so here in my little picture, I got an application and it's talking to the database. And the two main ways the database encryption is implemented is transparent data encryption, or TDE. And what that means is the database software is encrypting the data before it's saved to disk. Another way is full disk encryption, and that just means a level lower, the operating system or the hypervisor, or say you're going to the cloud, their hypervisor will encrypt the data before it's saved to the disk. So the great thing about this is it's easiest to implement. You click a little button and the database or the operating system is encrypting the data. And Oracle and Microsoft SQL offer this. The cons is it literally only protects against physical theft of that encrypted drive. I mean, as far as threat vectors go, if somebody gets credentials, the data is decrypted for them. If you make a copy of this database, the copy is decrypted for you. So it's only if that drive is encrypted. So if your hard drive on your laptop is encrypted and your laptop's stolen, that's a fantastic way to protect your laptop. But on a hard drive in a database that's in a data center these days, that's not really the primary concern anymore. So it only protects against physical theft. And even kind of to put it, a little more emphasis on that, Postgres and MySQL don't even offer TDE. I think the community has just said, it's such a narrow thing to worry about. We're not going to worry about it, So the open source versions anyway. Of course, you can always buy a enterprise version where they add that. So going back to my grid, TDE and FDE protects against physical theft and none of the other attack vectors. And then I did the same thing for if the application itself is attacked. And of course, because it's transparent to the application, it doesn't protect against any attacks where the application might have the data that's been pulled out. So kind of just going, through that, I want to take a break here and see what people are doing right now. So the options are no encryption, I should say. What's the poll? So what encryption have you implemented or plan to? This is obviously about encryption, but feel free to answer. These are anonymous. I just kind of ripped on TD and FDE, but of course, if that's what you have, that's fair. And then if you're doing anything else, if you have a database plugin, if you're trying to implement encryption at the application, or if you're doing homomorphic encryption, we'd love to see that. Let's see here. So we're getting any, check the poll here. So the initial numbers here are about 40% say TD FDE. That makes sense. It's pretty widely implemented, even though it has the issues we talked about. 30%, which is a lot. Well, maybe it's because this is about encryption, maybe not, but it's another 30% says no encryption implemented or planned. And then 20% are trying application encryption. 10% are trying a plugin like PG Crypto, and nobody's trying homomorphic encryption, which that'll make sense as well when we go into this more. So the application encryption, I think we're going to go into that one next, and that's where probably a lot of people are running into issues. So go ahead and jump right into that. Well, actually, sorry, I'm going to take a step back and go through the goals that we're want to do, and then I'll talk about application encryption. So our first goal is to minimize data security by implementing encryption in a way that minimizes the threat vectors using the concept of least privilege. So all those threat vectors I talked about, how do we knock as many of those off as we possibly can? No application code changes for ease of implementation. So if you want to do application encryption, now there's got to be code changes. And what if it's, which that all by itself is a lot of work, right? You got to make the changes, you got to test it, you might have downtime. And then on top of that, what if you have legacy code where the original programmers are no longer around? What if it's in a language that none of your current developers are familiar with? There could be a lot of issues there. And then if it's commercial off-the-shelf software or third-party software, you can't make code changes. So it's not even possible in that case. So we want to be able to address that. We want to centralize the encryption policies and the key management while enabling bring your own key or hold your own key. And so it is really important that all your encryption policies and key management be centralized. Otherwise, if you have different teams and different tools doing it, there's going to be conflicts, and it's going to be almost impossible to audit and show your auditors that you have everything in place. And then finally, we want it to be highly performant and conform to existing architecture for business continuity and disaster recovery requirements. We don't want to have to implement this new system that completely disrupts your current infrastructure, and then you have to go back and rethink everything. Like, how do I handle availability at that point? How do I handle disaster recovery? So we don't want to mess with your existing architecture. So those are our goals. And then I'm going to go back to application-side encryption. And that's just like the picture shows here. Now your application is doing the encryption and decryption before it sends it to the database. And the great thing about that now is no matter how your database is attacked, it's protected. So that's the pro. The cons, however, I kind of alluded to this, is now you need significant code changes for all your encryption and key management, right? It's not only difficult to know how to implement encryption properly, but now you have to determine what needs to be encrypted at with every application, how it's encrypted, and how the keys are done. So now you have no centralized management for coordination and auditing because every application is doing this on its own. It's hard to implement least privilege, and I'll talk more about that, on the application because now it has all the controls. So how are you going to ensure that the user of that application or even the application itself doesn't have all the access to all the information? And then finally on this is all the operations on any encrypted data. So let's say you want to take the sum of all the salaries, or probably more specifically like the average of all the people's salaries. Now your application has to download every piece of salary information from the database, decrypt it, perform the operation, and then release it. And so now this adds to the code changes, but it's also kind of defeats the purpose of encryption in the first place because now the data can go a lot of different places. So when we look at it, like I said, it's fantastic from the database attack perspective. Your database is protected. However, it doesn't offer any protection from the application attack. Plus you have all those issues with how to implement it. So the transparent application level encryption approach, I'll just be straightforward. This is Baffle's approach. And so this is how we go about doing it. So let's say this is your starting point. Let's say like 40% of you have your TDE turned on and it's encrypted on the hard drive, but it doesn't matter if that's on or not in this case. We're saying, look, you have an application that can talk directly to your database. So that's where we're going to start. Then we take this proxy and we drop it right in between them. And at the highest level, the purpose of this proxy is to encrypt anything that's written to the database and then decrypt anything that's pulled out and apply access control to your application. So the great thing about this is it's at the network level. Your application cannot see it. It's invisible to your application. All you do is change your connection string from directly to the database to the proxy, and there's no application code changes that result from this. Then the next thing we do is we handle all the key encryption. So we implement a two-tiered encryption method where there's these data encryption keys that actually encrypt the data itself, and then there's key encryption keys which encrypt the data encryption keys. So Baffle is able to centralize all the control of the keys, but we also allow customers to implement their own management of the keys and even creation of the keys if they want to. So we can connect to an HSM, we can connect to AWS KMS, HashiCorp Vault, Google Cloud Key, Azure Key Vault. You have control of your keys, and even if you have a SaaS, your customers could have control of the keys. If you remove those keys, all the data is effectively shredded. So you have control of the keys themselves, but we actually do the management of the mapping and provide a centralized place where it can all be controlled and audited. Well, we also have something, a management console that we call Baffle Manager. It's responsible for all the configuration and monitoring of the proxy. Whoops. And the last thing on this is both the management and the proxy are implemented as containers. So you can use, the old-fashioned, just put load balancers in between there and sensing to see, to make sure that your high availability and your disaster recovery stays in place, or you can implement a container management system like Kubernetes. And now you have the ability to mirror however your backup plan is for your database. So if you have one read write and many reads, your proxy can just follow along with that. If you have all this completed in another area for disaster recovery, you can just mirror the exact same copy. And also, if you're using container management, you can scale this automatically. So you can have one proxy in there for kind of your baseline, and then as your availability requirements go up or as your usage requirement goes up, you can automatically scale more proxies. So that is solving that goal of not changing your architecture and going along with whatever BCDR you have implemented. Okay, so I talked about it's transparent application side encryption. So the great thing is we still have all the database protection. We got rid of the code changes because it's transparent to the application. The centralized management's taken care of, and we can apply least privilege to those applications. But the one thing that still stands out is operations on the encrypted data still requires a download of all the data, decrypt it, and then perform the operation. So we're going to dive into this specific issue and how other people have taken care of it. But first, we're going to talk about, or we're going to have a poll here that is, what is preventing you from implementing encryption? So nothing, you're done. You've already implemented encryption and you're satisfied. Or you're just getting started. Have you had any application changes that are stopping you from implementing application-side encryption? Is it just a pure cost, time, and resources thing? Maybe you're being held back because you're unsure of the best method, or you believe that all the access controls you have right now are sufficient. So let's start that one. Let's see here. So, all right, looks like the cost and time and resources, 43%. So that's a big deal, right? Like if you got to make application changes, or even if you don't have to make application code changes, security is always involved a lot of different people, a lot of different change control. So, that kind of makes sense. I just jumped up. So about 50% are cost and time resources. Another 25% is nothing's holding us back. We're just now trying to get started, which is maybe why you're on this call. 13% says we're not going to do anything, which is fair. And then another 13% says alternative access controls are sufficient. So that probably goes along with we're just not going to do anything. We think we're good now. And then it says nobody says that because the application changes, but I think that goes along with the cost and time resources anyway. So, okay, that's a cool poll. All right, so that final problem of operating on encrypted data. So how is that being taken care of? And so it's often called privacy enhanced computation. The problem is when I want to do something like take an average or do sort or cert or whatever the case may be, I have to pull all the data down, decrypt it, perform the operation, and now that decrypted data is at least temporarily in the wild. And so there's an entire area of research and an even industry of how do we enable encryptions or operations on encrypted data. I'm going to step through 4 of the alternatives and then talk about what Baffle does. So the first alternative I'll talk about is homomorphic encryption. Then we'll talk about secure multi-party computation, structured encryption, and secure enclaves. So the first thing is homomorphic encryption. So what is it? Homomorphic encryption is encryption implemented in such a way that computations may be performed on the encrypted data, and then only the result is decrypted. So in my little example here, let's say we encrypt 100, 200, and 300, and we get these results, the 234 and on. And if it's homomorphic encryption, you can go ahead and you can tell the database, add those values together and report back with the result. And then whether it's, wherever the decryption happens, whether it's in the database or the application, we can now get that result, decrypt it, and it actually ends up being the same as if you added all these together. So that's the basic idea of homomorphic encryption. So the pro again on, we go back to our matrix is any database attack is protected. Although I do have an asterisk and I'll talk about why on that. However, application code changes are likely because either the application has to implement the homomorphic encryption, or even if it's implemented in the database, as of right now, mostly it can only add or multiply, add, subtract, multiply or divide, I should say. So say if you want to do average, your application still has to know, okay, go ask for the sum and the number, and then when you give me that information back, the application will actually divide the sum by the number to get the average. So there's still application code changes. There's no way to do least privilege, at least if you do, it's with other tools, right? You can always add other tools, but as far as homomorphic encryption itself, there's no addressing least privilege for the application. It's unknown if sort and search are possible. So, okay, that's a really cool trick that you can add all these together and decrypt and get the same result, but they aren't going to sort and search in the same manner. So, there's research going into that, and then they'll have to do more changes to the algorithms to see if they can get that to work. The biggest thing, and probably the primary reason, well, I know this is a primary reason it hasn't been implemented, at least beyond little niche applications, is it's orders of magnitude slower than non-encrypted queries. I mean, orders, not like 10 times, but like hundreds, maybe even sometimes thousands of times slower than non-encrypted queries. So that's the biggest reason it hasn't been implemented. And then the last thing, I had the little asterisk on any database attack is protected, and that's because the encryption algorithms are not standardized. When we talk about encryption, there's kind of 2 schools of thought. One of them is I should keep my algorithms proprietary so that way people can't go through and easily reverse engineer it and find weaknesses. And then the other school of thought is I'm going to make the algorithms, open source, let the whole world see it and have them attack it. And then if somebody, can break it, then we'll know about it. And I think the former one is kind of lost in the last few years, actually a long time. And we've kind of been more to the open one. So you can go to NIST and you can look up AES encryption and you can find out exactly how to do it. And thousands of people worldwide have attacked that thing and they can't break it. You can't say the same thing about homomorphic encryption because there's lots of different approaches that have been tried and nothing's really been standardized or settled upon. So that's where homomorphic encryption is. The next one is called structured encryption. And now instead of being able to do the operations directly on the encrypted data, they're saying we're going to perform operations and pull out metadata and add that to the information, to the encrypted text, and that will allow us to do sort and search. And actually, our friends at MongoDB are in the middle of implementing something like this for their NoSQL server. So, the pros are any database attack is protected, but it has a similar asterisk in my mind because, those encryption algorithms, I don't know if they've been standardized or not, and they certainly haven't been under as much scrutiny as, say, AES encryption. And it makes a lot of sense for NoSQL because the critical thing for that is sort and search because you have files, and then that metadata can just be incorporated in those files. So it makes a lot of sense for that. But in SQL, where you want to do computations, it's actually unknown if computations are even possible on that. I always talk about the application least privilege. You can add that, but it has to be through other tools. And then when you're actually creating this metadata and doing writes, it can make those writes 5 to 10 times slower. And this is off MongoDB's the information that they've provided publicly. And then the storage, because you have to incorporate that in your database, can increase it up to 5 times. So if you have a terabyte of data before it's encrypted, after it's encrypted, it may be up to 5 times as much. So those are the pros and cons of structured encryption. Another approach is secure multi-party computation. And so here the idea is you take the data. I guess originally this was meant for like when you had several different parties or organizations, and they didn't want to share data necessarily, at least the privileged data, the sensitive data, but they wanted to be able to do analysis on it. So like if it's 3 different marketing firms, instead of looking just at their data to try to figure out the entire market, maybe if they incorporated with their competitors, then they could all see what the size of the entire market is, but still have no idea what each individual share is. So what they do is each individual one, let's kind of change a little bit. Let's say these are individuals and they want to figure out what their average salaries are, but they don't want to share their own salary. So the first person could write in here and that information is split up and say that first person makes $100,000. You can put in the first database $5,000 and then the second database like $60,000 and then the third database $35,000. So no one location has the actual information. And then you can do the same with all the others. And then when somebody does try to do an average, they say, okay, give me the sum and give me the total number of people. And you pull that back and all those are added up. So no individual salary is given, but the total is. And then of course you can have the count and then everybody can know what the average salary is without knowing any individual ones. And then how this translates into an individual company is you would have just one, application here, but you would still break this up such that each, any single database attack would be protected. And then they encrypt on top of that. So there's, pretty complicated. It's a great idea, but again, let's go through the pros and cons. So if any single database attack is protected, so that's pretty solid. And then the whole point of this is application least privilege. So it does give that, the whole idea is any individual can't get the other people's information. But you got to decide where this is going to be. Is it going to be an application? Is it going to require code changes? It's almost guaranteed to need different coding. This processing, even though it's a lot faster than homomorphic encryption, is still a lot slower than just unencrypted queries. And then the biggest thing is it's a super complicated system. Like look at the cost of this. How are you going to triple your databases? How are you going to maintain this? How are you going to implement your business continuity and disaster recovery to this? It's going to be very disruptive to your entire system. So that's secure multi-party computation. And then the last one we'll look at is secure enclaves. So the idea here is the encrypted data is pulled out into specialized hardware, decrypted, the operations performed, and then only the result is sent back. So if you can imagine, you could implement this on the CPU of your database, and Intel implements this into some of their devices. It's called STX. This would be definitely protects against a database attack. I should not have had single database. It would be any database attack, and it's highly performant because this hardware is specifically made to do that. So it's going to have those advantages. The cons is, application least privilege, which I talked about. The applications still get access to everything. And then the biggest thing is it's hardware. So how are you going to initially implement this? How are you going to get your database to now recognize that a query has been made such that it has to send the encrypted data here and just get back the operation? It's going to cost more because now you have to have like specialized hardware, and it's going to be difficult to scale. You can't just pop up another server. It has to be another server that has the same hardware on it. All right, so those are the alternatives. And now we're going to look at transparent application level encryption. And I talked about how we implemented this before, where we put a proxy in here and we took care of all the other issues of code changes and keeping your centralizing your policies and keeping your architecture. But if we stopped here, we would still have that same problem of, let's say we wanted an average age, min, and max for all the people with salaries over $100,000. Like it would break right on the sort in the first place, but then it doesn't mean anything, you know, average or sums of encrypted data. So what we did was added some extensions to the database. And now the proxy can talk to the extension, and I'll go in a lot more detail on this if we have time. But the main idea is when the proxy sees this, it says, oh, okay, you're trying to do operations on the encrypted data. So I'm going to break that down, and I'm going to communicate with this UDF. And this UDF is going to user-defined functions. I guess I'll call them extensions, but either way, extensions are user-defined functions. It's going to pull that data out in database memory, decrypt that data, perform the operations, and then send only the results back. And we call this real queryable encryption, and this is how we solve that final problem with application-side encryption. So now when we go through the database attacks, we talked about how TDE and FDE only protects physical theft. Application encryption is fantastic as far as protecting the database, but has all those other issues. The privacy-enhanced computation either makes things slower or is more complex. But I have the asterisk on protected because they might be using algorithms that haven't been fully attacked yet or fully matured maybe. Here, real queryable encryption protects against all of those. Now I mentioned this one special use case that I pulled out, even though there were no threat vectors mentioned in the IBM report. The person who's really paying attention could look at this and say, you know what, if I attacked your database, if I could get in there and pull the memory while this is happening, then I could exfiltrate the data and it would be unprotected. So while that's true, and I wanted to be open about it, think about if somebody had the ability to do that and they were doing this remotely, they've went through every network access control you have. They went through every server control you had. You were able to download software that could pull the data, and then you were able to exfiltrate the data, and you had to have the timing perfect. So while it's a theoretical threat, I don't think it's a very real one. And then if somebody had physical access, they would have to like solder memory probes directly to your RAM and be able to pull the data. So, it's there, but I think compared to a lot of the other trade-offs of the other things, this is pretty good. And then duplicate environments. When you encrypt the data, the encryption follows it as opposed to any other access control where the access control only works in whatever environment they're in. At this point, I want to kind of shift gears a little bit and talk about compliance and least privilege, because I've talked about how the databases can be protected, but I want to talk about how we can protect, like what we're protecting against, and how we can also apply that to the applications. So when you look at any security or privacy framework like PCI or HIPAA or GDPR, they all say you have to find your data and control it and implement this concept of least privilege. And even if they don't use those exact words, the idea of least privilege is you have access only to the data needed to do your job. And I have some snippets here where they come out and say, like PCI, it says, access based on a user's need to know. HIPAA, allow access only to those persons or software programs that have been granted rights. And later on they say rights because they needed to do their job. Same with GDPR, there's a controller, there's a processor. The processor is not allowed to have any access to data that the controller doesn't explicitly say they need access to. So that's all around that. So the ironic thing to this is if you think about your database admin, they have access to everything. They have access to all your employee information. They have access to all your customer information, finance, product, marketing, your confidential information, basically everything. But at the same time, nobody's going to fail any of these because their DBA has access. It's a glaring hole, but like, if you think about it, like, well, how is my database administrator going to do their job if they can't get access to the database? There's another aspect to that. Like, let's say, okay, you passed all your compliance reports and you want to migrate to the cloud. And then either legal or your risk team comes in and says, forget it. You're not moving your information to the cloud. And they're going to come right out and say, this also came from the IBM cost of data report. We don't trust the cloud. 82% of breaches involve the cloud. And we opened with Snowflake. Snowflake's in the cloud. So even if the compliance and security frameworks don't stop you, your own legal and risk teams may stop you. So if you implement application-side encryption, the database is protected. So your DBA can still have direct access, but they can do all the things they need to do. They can implement patches, they can create new tables, they can create new users, they can provide access, everything a DBA would do. But if they actually try to get the data, it's encrypted. The other aspect is the cloud provider. When I start an RDS instance in AWS, I can go look at the users, and there's this RDS admin in there. It's generally not going to be a person. It's going to be a service account because they've automated all this. But regardless, if somebody gets access to that, if your database isn't encrypted, then they can also get access to the data in theory. And this also goes for cloud misconfigurations, one of the other threat vectors on there, right? If you for some reason you left your database open to the world, it's encrypted. So that takes care of a lot of the hangups we have. One of the big holes even in your security and privacy frameworks, and then the other reasons maybe people may not want to move to the cloud. If we look to the other side, I've only shown one application hooking to the proxy, but in reality, you can hook as many applications you want to the proxy, or you can have different instances of the proxies and corresponding to the applications. But in this case, we're going to say, okay, because it's already in line, we can add access controls, both role-based access controls based on who's accessing it, and attribute access controls, at least the IP address. So let's say we have human resources. It's on one set server. So we said, okay, only people connecting from the server IP address, and human resources. If they request a credit card number, there's no reason human resources should have a credit card number. We're going to fully mask that with confidential. However, they do need social security numbers to do their jobs because they have to provide people with pay and benefits. So we're going to let them have the social security number. And then in support, we don't know where the support server is going to be. And there might be several instances. It might be scaling up and down. So we're going to say, like, if it's in this subnet, then they can have access. But we're going to mask everything such that only the last 4 digits are shown. So credit card number, social security number, and that is needed because support needs to be able to identify the customers that are calling in and needs help. So we're protecting it that way. And then this remote user, they may have access to all the other data, the non-sensitive data. But if they're logging in from some unknown place anywhere on the internet, we can give them access to that. But we're going to say, look, if you're remote, we're going to completely block your confidential information. You have to come to the office and you have to log in as one of these guys if you want more. This really goes back to that whole idea of least privilege. And it's also another term that goes along with this is limiting the blast radius. So if somebody did attack your human resources, yes, they got all the social security numbers, but they didn't get the credit card numbers. And you could have also encrypted the names as well. Well, human resources probably need the names, but you get the point. It's limiting the damage that can be done. With support, you could argue that you protected the people. Even though the last 4 digits are there, the credit card numbers and the rest of the social security number isn't there. And kind of going a little bit deeper, I guess I should have said that we call this dynamic data masking, but diving into PCI a little bit, PCI is great for me because I know the most about it, but also because it's the most prescriptive. The other ones just say, apply access controls. Encryption can be one of them, but they have to be proportional to the risk of the data. Okay, but PCI says, forget that. You're going to protect credit card numbers, and here's how you're going to do it. They come right out in one requirement and say, FDE is not sufficient. You can use it, but you have to have other controls if you're going to use it. So that's one aspect. And then they say, a lot of credit cards, exactly like I said, for support, maybe they need the last 4 digits to identify the users. But also within, if you're doing payment processing, you might need the access to the first 6 digits. And that's like tells you who the issuer is, like Visa or MasterCard or Amex or Discovery. And it also says what bank issued it. So, Bank of America, Chase, or Capital One, or whoever. And so you might need that to route the information, but you don't need the actual full credit card number. So they talk about masking. And if you implement something like FDE, you need additional tools to implement that, whereas with Baffle, it comes with it. And so this kind of puts a fine point on that application attack. None of the others incorporate that. But with Baffle, you get the dynamic data masking with it. All right. So, I don't know, Sean, do you think we have time to go into this one, or?
I think we do. We're pretty much on track, so I think we have time.
Okay, fantastic. So I want to just talk a little bit more of how we implement our QE. So I'll try to keep it at a higher level. But for those of you who are curious, so here's the picture of the application, the proxy, and then the database with the extensions or user-defined functions on there. So when we break down this proxy, we're literally putting it inline in the network. So we're intercepting the ones and zeros to the electrical surges coming in, turning it into bits, and then this first network stack, what we're doing is pulling off all the like the routing, the TCP IP layers down to just the message. Still bits, but we're ripping off all the extra information. And then in the message, we're decoding the actual message and breaking it down into the actual SQL queries. From there, we take those SQL queries and we have to make a decision. The first decision is if it involves data that is not encrypted, just pass the query right on through. The second one is, okay, does it involve encryption? And if it's encryption, but it's an exact match, like, I'm writing a social security number, please encrypt it before you send it, then we do that and we put the encrypted data forward. And if it's a query that's on the encrypted data that already exists, like I talked about, if we want to do a sum or average or something, it will pull that, rewrite the query, and put messages in the UDF that says, hey, here's what I need you to do to provide that. You need to pull this data, you need to perform these operations, and then send me back the results. So that's put in there. So we package that up into this new set of SQL queries, turn it back into bits, put all the other network stack stuff back on, and then send it down the line to the database. On the way back, we have to do the reverse. So we strip off all the extra stuff, take it down to the SQL query, and now, or it's not SQL query, on this side it's the results, right? So now we gotta look at the results and again, make decisions. If it's already plain text, we can just send it on through. If it needs to be decrypted, then we do that. And if there's any, I guess that's probably it. Those are the only two things on this side. The third thing here is the RBAC enforcement, right? Does this person who's connected, do they have the right IP? Are they the right role? Do we have to block them? Do we have to let them see everything? Or do we have to mask them? And so that's done there. And then we bundle that back up into bits and send it down the line. So that's the proxy. The extension, when we connect to it, a lot of people will ask like, oh, what if I alter the extension? Or what if I put my own extension here and trick the proxy into connecting? So we put a lot of effort into setting up the initial connection. And what we do is when we connect, we say, okay, take a hash of yourself and send that back to us. And that'll tell us immediately if it's somebody else's extension or if it's been tampered with. And assuming it passes the hash, then we say, okay, we're going to connect. The next thing we want you to do is create an ephemeral encryption key. Send that to us. Then we'll encrypt the data encryption key and send that back so that it has it so that when it needs to do the decryption. So that's how we protect against any attacks on the extension. And that's how we get the key over to the UDF. And it's ephemeral, so like we'll release it when we actually send it over when we need it, and then we release it as soon as it's done. Within the extensions, we have to have this user-defined type, and the whole purpose of this is to translate between whatever the clear text data type is. Whether it's a string, is it an integer, and if it's a string, is it a varchar, is it text? If it's an integer, is it or is it if it's a number, is it an integer, is it a float? Whatever the case may be, we have to map that over to the encrypted side, which the encrypted side is, if it's traditional encryption, are always it's binary. So we have to keep track of that, and that's what this user-defined type does. And then the next thing in here is the functions themselves, where we tell it how to, pull the information and do the decryption, and then we actually perform those operations, whether it's hashing, greater than, less than, equal for indexing. It goes on. There's lots of different user-defined transforms that we do in there. Here's some examples. So when I mentioned the proxy has to pull that information and transform it to send it to the UDFs. So here we have an encrypted column, and it says, okay, yes, it's an encrypted column, but it's not an integer anymore. It's this new baffle control 2 user-defined type. If you're inserting something, okay, it's an encrypted column, so we have to encrypt it, and then we send the encrypted value instead of the clear text one. But in this other column, it's clear, so you just pass it through. It goes on. We can index. The nice thing about that is it's handled by the on the PGTLE side, which I'll talk about that in a second. So this is a small sample of those transformations that are happening in the proxy and talking to the UDF. Another thing is, how did we implement those UDFs? And originally they were written in C and C++. And for on-premises or any self-managed one, like let's say even if you went to AWS and you implemented on an EC2, you're self-managing the database. This is great because it's high performance, has high performance capabilities. The problem with this is if you go to a managed database like AWS, RDS, or Aurora, they don't allow C++ extensions to be added. And that's because it's very powerful language, but it has access to the kernel. So it doesn't do things like data type checks, or it doesn't do things like make sure that the memory is if you tell it to do something with memory that causes the server to crash, it'll just do it, and then your server goes down. So the managed database providers didn't want to have to deal with that, so that's why they blocked it. So then we're like, well, how can we provide these services to managed databases? And one of the things they did allow was procedural language PostgreSQL, which is it's SQL, right? PostgreSQL. And so because it's a high-level language, it has all those protections in there, and it's limited, and we could implement that. The problem is it's super low performance. It does hamper our speed in a noticeable way, so we had to kind of get away from that. I mean, it's high compatibility, meaning you can use it anywhere, but it really affected performance. And then AWS came along, and they wrote something called PGTLE, which is Postgres Translation Language Extensions. I might have got that wrong, but anyway, it's an abstraction layer which puts in a lot of protections from crashing the database. It kind of takes away a lot of that kernel level access. And then on top of that, if you use Rust, it turns out Rust is just as, or at least close to as performant as C++, but it also has a lot of protections of its own. So now, if this is implemented, it's high performance, and you can use it with managed databases. And so this is how we implement it on AWS, RDS, and Aurora. All right, so the next part here is real queryable encryption. So I'm going to go ahead and switch screens here. Sure. Okay, I hope people can see my PG admin dashboard. Okay, so there's basically two parts on here. There's this top part that's highlighted here is a connection directly to the database. And then the other part here is a connection to the baffle proxy. So the purpose of showing the connection to the database here is I'm going to go ahead and select and look at the information there. And so here we have a table with a identifier, primary key, first name, last name, and then social security, age, and salary. And you can see that they've been encrypted with AES. This is the hex version of the bits that would be there. Right? So it looks like a completely random string, except for it starts with baffle there. So it's encrypted within the database. And again, if the database is attacked, it's perfectly safe. Now, if we go over to the connection through Shield, and I do the same thing, oops, I like that. Now all the information came back decrypted. Now, I thought of this late. I should have masked the social security number and even maybe hid these to show our dynamic data masking. But in theory, you could have, like let's say you got a data analyst. There's no reason for them to see the social security numbers because they're just going to do crunch numbers on the age and salary. So I could have blocked these off or even just shown the last four. Maybe next time I demo it, I'll do that. But let's say we have a data analyst. And these are exact matches. So it just comes back, and this would work with any application level, right? Where you just ask for the number, it comes back and they decrypt it. However, if I was going to do an average on this, it would break it without real queryable encryption. So here I'm going to say I want the average age, min age, max age, and from any of the employees where the salary is over $180,000. So if I go ahead and do that, this is where the proxy saw that, said, okay, I'm going to break this down into different queries, send it to the UDF, and then get back the results. So the average for anybody who makes over $180,000, the average age is 62, their minimum is 50, and the max is 75. So this is the final issue with application-side encryption that Baffle has solved. And then I'll do this other one where we're doing a sort, we'll sort by salary from lowest to maximum. And so again, this can be done within the database without pulling all that information into the application and exposing it there. All right. Let's see here. How do we cancel this? Stop sharing. All right. And so for our last poll here, just curious, would you like to try a demo of, or see a demo of real queryable encryption? All right, cool. Like a lot of people want to see it. So with that, I'll go ahead and turn it over to Sushant.
Great. Thank you so much, Billy. Hopefully this was very informative. So folks, I just want to summarize, and before we hit the Q&A, we do have a couple minutes, and if you have questions, please put it not in the chat. I do see some people point in the chat. It'd be great if you could put it into the question widget, but it's not a big deal if you can't find it. We'll get it off the chat. So a couple things. We leverage Postgres extensibility to make the easiest implementation of encryption, right? That minimizes all threat vectors, right? If those of you who have been kind of think of same old with the Snowflake data breach, it's not so much that cloud services are insecure, it's that there's more threat vectors, as Billy has talked about. And so you got to start with the data itself by cryptographically protecting the data. Even if you get breached, someone that gets access to your encrypted data, it's a no-op, right? It doesn't matter. This should be one of the key principles that you have is all your PII data should be encrypted with role-based access control. If you have that as the standard, the likelihood that you will end up in the news for having a data breach is almost next to zero. Let's see. When we talk about the proxy and extension architecture, you get encryption, masking, multi-tenant access control. And here's the key: no application code changes and compatibility with your existing architecture. One of the ones that people often forget is third-party applications. If it's an application you control, sure, you can go through and make code changes, and that only gets you so far, but you probably have data in applications that are third parties. Think of something like Tableau. By having this no application code changes, you can make sure your data is protected not only in applications you've created, but also in applications that are third parties. We make the encryption policy, key management, access controls based off least privilege and auditing. Auditing is actually pretty important. You need to be able to prove to your auditors that you have technical controls so that they know that you've protected the data. They don't just take your word for it. That's a good way to get fired by an auditor to get fired if they just take your word for it. You need to be able to show and prove. Lastly, we enable broader enterprise usage of Postgres. One of the things that you may see is if you compare the data security capabilities of Postgres with Oracle and SQL Server, again, legacy databases, they actually have a lot more data security capabilities. And then this becomes a concern for InfoSec and cybersecurity when they say, well, when you want to use Postgres, well, it doesn't have all the data security capabilities. So is this going to be safe? And with Baffle, we make Postgres, and we can even show it to you, have actually more data security capabilities than even the legacy vendors such as Oracle and SQL Server, and we're happy to show that to you. And this includes self-managed and also AWS RDS and Aurora deployments. So with that, let us go try to hit your questions. But if you'd like to get a live demo and meet with a Baffle security expert to qualify your data security needs and then try RQE for yourself, we're happy to set up a POC. You can try it for yourself and see if it meets your needs. You can, if you have your phone available, pull that up. It'll take you to essentially set up a meeting or request a demo, or you can go to baffle.io, and in the top right-hand corner, you see Baffle. You'll see request a demo, and you'll get that. So let's talk about some of the questions that you folks have. And I think we have a couple one. So here's a question. Billy, it says, you mentioned homomorphic encryption in orders of magnitude slower. What's the performance impact with Baffle?
Yeah, so that's a good question, and it's really difficult to answer because it depends on how you do your benchmark, and it also depends on how you implement it. So with Baffle, you can choose every different column that you want to encrypt. So if you only encrypt a small subset, it's going to have almost no impact on performance. But if you have a lot of data and you encrypt all of it, that's going to be a very different situation. So much of it depends on how it's implemented. But what I can say is with all the customers we've implemented with it so far, they haven't seen any impact, right? Like, especially in human scale, right? So like if, as you're a human and you're watching it and you get it back, the impact to Baffle is going to be imperceptible. Now, obviously, if it's like more automated scale, you might see something, but it's definitely going to be a single to less than 20%. 20% would be if you encrypted everything and you had a maximal database thing, but like nothing compared to like homomorphic encryption, where it's orders of magnitude slower.
All right, probably have time for one or two more questions. Here's a question. Are only number columns encrypted by the Baffle proxy? I see text and varchar not encrypted in the demo table. Oh yeah,
so you can definitely encrypt almost any data type, whether it's string or numbers. There's traditional encryption. You can do AES deterministic, which turns any data type into like a random looking bit stream. You can also do randomized. So every different time it's encrypted, it gives a different value, although it always decrypts back. And then there's something called format preserving encryption. So if you want to encrypt names, but you still want it to look like a name, you can just convert all to numbers. So like Billy would be transformed to, like ACXZ or something, but it would have the same length and be the same type. Formatting preserving encryptions for like credit card numbers is fantastic because the credit card numbers look like credit card numbers even though they've been encrypted. It just changes the numbers in this case. And we even have it such that if you pass the Loon algorithm on the encrypted text, that allows your any application that's using that encrypted data. Let's say you have a test environment and you have an application that's using these encrypted credit card numbers. The application wouldn't even know. So there's a lot of different variations we have that I didn't get into on how you can encrypt it.
All right, so we have more questions, but we're actually out of time. For those of you we weren't able to answer your questions, please do set up a meeting. More than happy to address your questions, and we'll try to follow up with you as well. And now let me turn it over to Hormaz for a final wrap-up.
Okay, well, thanks everybody. As a reminder, you will be getting an email shortly with a link to the replay for the webinar. Please feel free to share the webinar with your colleagues and friends. And I would like to thank you guys all for joining us today and making this an interactive webinar. Thank you to our speakers, Sushant and Billy, for sharing their insights with us. And we hope to see everybody on our next webinar. Have a good day, everyone. See you next time. Bye-bye.
Thank you.
Thanks so much.